cross-domain multitask learning for object detection and saliency estimation. In spite of state-of-the-art performance of deep neural networks, DNNs are often over-parameterized. The efficiency and compactness play an important role in order to run these models on mobile devices. To this end, we propose an MTL architecture that jointly performs saliency estimation and object detection. We also analyze the effect of parameter sharing in multitask learning architectures for reducing the model parameters and memory footprint. The absence of a suitable dataset with annotations for all the tasks poses a serious problem in an MTL paradigm. Therefore, we enable MTL frameworks to utilize ground truth annotations from different domains for learning different tasks, calling this setting as cross-domain multitask learning. In an MTL setting, to improve network performance, it is important that the tasks in the task set are closely related to one another. This relatedness can be measured using representation similarity analysis. From figure 1, we can see that the representation similarity analysis score for saliency estimation and object detection is quite low, making this a challenging task set to jointly optimize. Object detectors are broadly categorized into region-based and unified object detectors. Region-based detectors compute region proposals and then determine class labels for the computed proposals. Unified object detectors are end-to-end architectures that directly predict the class probabilities and the bounding box offsets in an entire image. Traditionally, visual saliency models were inspired by biological features captured via colors, edges, and texture in an image. However, with recent advancements in deep learning and availability of large datasets, we have seen more data-driven approaches that use CNNs, LSTMs, and even generative models. In this work, we propose an MTL architecture that jointly performs saliency estimation and object detection where the data comes from two different domains. We also adapt a bilinear kernel for learning domain invariant features. Figure 2 gives an overview of the proposed MTL network in a cross-domain setting. Inspired by its wide usage in domain adaptation, measure the distances between the two domains using maximum mean discrepancy, and its equation and its formula is defined in equation 1. Inspired by visual question answering and bilinear models, we propose a learnable bilinear kernel function whose formula is shown in equation 2. The loss term for constrained MMD is shown in equation 3, where the logarithmic terms are present for regularization purposes. The task-specific losses for object detection and saliency estimation are expressed in equations 4 and 5. The multitask objective loss function is expressed as a weighted sum of equations 3, 4, and 5. Figure 3 gives an overview of the detailed architecture with layer hyperparameters. We conduct our experiments on two popular datasets, MS-COCO and Pascal-S. All our experiments are performed using PyTorch on a machine with Intel Xeon processor and a Quadro P6000 GPU. We prepared two baselines, SSD 300 for object detection and MSINet for saliency estimation. The comparison against our proposed model is shown in tables 1 and 2. The baseline models operate at 36 frames per second, whereas the proposed model runs at 47 frames per second. Our model occupies 13% less memory and uses 40% less gigamax operations while running evaluation on one image. We compare the domain invariant performance of different CNN feature extractors in our model to justify the use of ResNet 50, the results for which are shown in table 3. We also investigate the effect of different saliency metrics in the saliency objective function, and the results are shown in table 4 for Pascal-S dataset. For object detection, we perform comparison on MS-COCO dataset with one-shot detectors, and the results are shown in table 5. Table 6 consists of recent saliency methods and their comparison against our proposed work on the Pascal-S dataset. Figure 4 shows some of the qualitative results of our model. In the future, we plan to extend the proposed framework to more complex computer vision tasks on multiple datasets. Thank you.